here on we do recording, and hopefully it works. Let me check again. That seems to be all right. If not, then, well, what shall I do, right? So we have, yes, screen is also on. Now here the annotation, and we can provide each plot with labels, axes, axis labels, graph, and annotations now. Font size can also be changed. 0.5. A little bit small, right? 50 would be a little bit large. So some nice font size somewhere in between. Not too big, right? Not too small. Readable is important. So what you should do, right? You make a figure, then you save a figure. How do you save a figure? You remember? Save figure, right? Give it a name. My important figure. Which file format is recommended? Recommended would be PNG or PDF. And then you save it. Okay, so this should be saved somewhere. How do you know that this text is large enough? You put it in your thesis, right? And then you print that page as A4, A3, or however you print your thesis. And you put it in front of you to check, is it readable or not? If it's not readable, right, then you go back and you increase the font size a little bit. Because in the end, when you make a figure, it's supposed to be used somewhere. So you need to check where it is used. Is it useful? Okay, so markers. So we revisit the scatter plot, right, and we explore the choice of different markers. Similar to line styles, right, or line types, the markers can be used to distinguish different sets of data within one plot. Now, why do we need to talk about markers? Well, scatter plots generally don't use lines. And the way to communicate the data is then with data points, which are represented with dots, squares, circles, empty circles, and so on. So let's see what we can do. We again have an example, and we use some random distribution of points on the x-axis, which are passed to some cosine function as y values with some added random numbers, right? Some random noise. And then I have here in line 7 the colors argument, where I say we make a rainbow. That is what it is saying. It scales the values of x between 0 and 1. So over here we multiply it by 3 pi. Down here we divide by 3 pi. My random function returns me values between 0 and 1. Multiplied by 3 pi is 0 to 3 pi. And divide by 3 pi is back to 0 and 1. Right? So this array here contains no values that scale linearly with the x values to be and are between 0 and 1. Now let's see where we use this argument, colors. Right here again, coding is British English. Sorry, American English. Now the colors argument array goes to the C argument, right, or parameter of this function. What we see, or the effect we see, let's explore. I'll take this, leave there, cut out. Always a little bit difficult with one hand. So without this argument given, we would have just blue squares somewhere, right? Distributed with a little bit of noise. And if we are very kind to this data, we should say, yeah, there's a cosine. With the colors argument, now we change going from left to right the values of color. We start with 0 over here, and at the end we add 1. And this is basically now going through a so-called color map that maps some values between 0 and 1 to certain colors in RGB. Okay. What else? Then we have area. And area here is given as numpy, absolute values of a sine for n. But n is 50, so this is just one number. We also see that the marker size is not changed, right? So let's go into the scatter plot. We have area times 900. Let's scale it down a little bit. Area times, let's say, 400. Okay, so the markers are a little bit smaller. Now I go back to my area, and instead of sine n, I put sine colors. Let's make it easy, sine x. Do you see what's happening? So now I start with relatively large squares somewhere. I have some small squares, larger squares, small squares. That is not really a constant anymore, right? To make it a little bit easier to understand, we just put size x. And we know x is increasing from left to right, so are the colors, right? Okay. So we start with tiny squares and we get really large squares at the end. Let's make it a little bit smaller, like this. What else do we have? We have an alpha value. Because if you look very, very carefully over here, for example, the yellow squares that overlap at around x equal 9. Right? They're like 1, 2, 3, 4 squares that are at the same position, aren't they? I don't want to change the data now. I don't rerun. I split the cell. How do I do this? Split cell. Right, so my data don't change now. I remove the alpha argument that regulates transparency. I execute again, and then I ask you, how many squares do you see here? I don't know, right? I see at least, well, 3, right? Because I see some corners, but just now we were lucky to have seen 4, right? 1, 2, 3, 4, yes. So this transparency helped me to check if I have very large markers, how do they overlap? Do I have more than one? Right. And then we have the marker style. As for square, maybe you like circles more, right? So we change it to an O. Okay, we can have plus. If you scroll down, there should be a summary somewhere. Oh, that is quite nice to see here the overlap region. Right. So note, color and size can be passed as an array, and then each data point can have its own particular marker size. That when you have a very, very large data sets, right, you can take them to distinguish your data. Oh, is this data from material A? Then you give it size 10. If these data from materials C, then you give it size 5. Or you want to represent some uncertainty, then you can also use the size as a contributing factor to represent your data. Or you use different colors. You don't have to use a continuous gradient as I showed you. You can really say, okay, you have a few big areas, and then for each feature value, you assign a certain color. Okay, so the alpha adjusts the transparency and color and sizes. For further properties, frequency, precision, and so on, right? We can select the sizes by the S argument for size, the color for a C, and either we give one value for all or different values. Let's go back. Size is over here. 10. Can choose the same size. Now 10 is a little bit small, maybe 60. Yes. So far, so good. So how do you know? Should I use an array to pass to these arguments, specifying the marker properties, or just a constant value? Always consider, what is my data about? What do I need to show? Is it enough to choose the same marker size, or do I really need to say, hey, for each different property I have different attributes? Okay. Here we have a collection of the different marker styles. I normally would recommend either you use point or circle, only one of the triangles. If you have too many different triangles, people will be like, it's very hard to see actually which triangle. So, right, you can combine a circle with one of the triangles, but if you combine different triangles, it gets a little bit messy. So try to choose only one. The triangles here I normally don't use. It's a little bit fuzzy to see. If you choose the circle, don't use the octagon, because the octagon almost looks like a circle. Let's see. Here's the circle. Here's the octagon. Can you see it's an octagon? Almost looks the same, right? If you now choose circle and octagon, it looks all the same. So don't do this. Combine only markers that are very distinct. Right? You can combine the square with the circle octagon, plus you can combine with the circle whatsoever. Don't combine the plus with the cross. Do we have the cross? Here there's a plus, capital P. Right? Is there the plus somewhere? Don't have. So we have here, for example, the plus symbol marker I showed you, or the capital one. They look almost the same, right? One is just very fat, the other one is very slim. But there are restrictions on what is meaningful and sensible and practical. But you have a few options of combining at least 5-ish kind of different markers in one plot. Right. So here again we have a table from the textbook summarizing the different features you can choose to modify markers. Now here is an example. Right. Example, marker sizes, or marker shapes. How many different data do we see? Well, it's in the legend, right? 1, 2, 3, 4. So we have 4 different markers, and here I use the dot, the hexagon, is that right? Marker, let me check. P, V, S, and H. H I think is for hexagon, S is for square, V is for triangle down, right? Here triangle down. And then P is for point. Small p, right? Not capital P. Let's see. Oh, pentagon, sorry. So this is pentagon, this is capital would be the fat plus. Okay, so I see definitely. So what do I see actually? What do you see in this data? So when we have a scatter plot, we want to explore correlation between data. What does it mean? There's correlation between data. What does correlation mean? I give you an example. It's a metaphorical example. Don't try it at home. Don't try it on campus. But find yourself a macaque. Macaque, the monkey. Oh yeah? Take an object. Give the object to the monkey. We are not feeding the monkey in real life. You're not supposed to do this. It's against the law in Taiwan. But let's say the object is a banana. You give the banana to the monkey. What will the monkey do? Be very happy, right? Eat the banana. Right? So you do something and there's an effect. You can measure this somehow, right? So there is basically, if you measure, I don't know, you give the monkey some object, oh, happy, right? How about you give the banana to the screen in front? Will the monkey be happy? Will the screen be happy? No, nothing will be measured, right? If you give many bananas to the screen, there is no measure, no effect, right? That means if X would be the number of bananas and Y would be the happiness you measure, the screen doesn't care about bananas, flat, right? If you give one banana to the monkey, a little bit happy. If you give 3 bananas to the monkey, very happy, right? Or more monkeys are happy, I don't know. But basically more bananas mean more happiness or more, I don't know, eating, more full food, more fat monkeys. Anything you can measure. So you would see, okay, the more you give, the more you measure. That is a direct correlation. How about if you measure something else, something inverse proportional? I know, the more, I don't know, do you go sometimes to McDonald's? If you start feeding McDonald's to the monkeys and you measure the health of the monkeys, that would go down, right? Same with you, by the way, right? Don't eat too much McDonald's. So you give more and more McDonald's to the whoever, right? You measure the health, go down, negative correlation. So when we explore data, we normally want to see some trend, either go up, go down. The worst thing we can observe, well, the worst thing, the most interesting one is flat distribution, right? Because that doesn't respond at all. Now, right, don't feed the monkeys, don't eat too much McDonald's. We go back to the class topic. Correlation, plotting. So in this data, it's a little bit messy, right? Because we have a lot of distributions. In a scientific work, you probably would not give it like this. You would separate it a little bit. But if we just focus on a few data at a time, we can now explore in the scatter plot, for example, that the red dots, right? If we just focus on the red ones, they're kind of random, right? So they are like distributed, but there's some up, there's some down, there's up, down here, down here, up here, down here, up here. It doesn't really seem that there's a trend pointing up or down. There's a lot of noise, right? The noise stays there because I have introduced the noise. Let's see. Random points, red. Right. So if I remove the noise and I make it really linear, so that would be a fancy correlation here, right? A straight line. But because my distribution is just some random points, there's no correlation. Now these examples are constructed, meaning yes, there is a randomness to this because the data itself are random data. And two random functions are definitely not correlated to each other. Right? If I have one random distribution and you have another random distribution, there's no relation between them. Now, the black dots indicate strong correlation. You actually can see this, well, more or less clear. Do you agree with me that there's strong correlation in the data? There's a little bit of noise. What we see on the left, the values both have negative in x are negative in x and y, and we follow more or less the points as they go up. There's a little bit of noise, but they go up all the way until here. X equals 4 and y is almost 4. So that would be a strong correlation. We have a weakly negative correlation. That is the blue one. And we have a weak positive correlation that is the green one. And they all fit in the same plot with scatter. Even if you put them now black and white, they would be distinguishable. Shall we try? Where's my... Here. Distinguishable, yes. Easy to distinguish, no. Change all to black, because we have many, many points. Ha. You know what to do? Tell me which is the weak correlation, which one is the strong correlation. Don't look at the legend, right? But in principle, if I really focus, right, now just on the dots, I still can follow them roughly. It takes a little bit of practice to now see the random distribution, which is the hexagons that are everywhere, that overlay with the other correlations. Let's see. Cancel that out. Right, and if you take away the random data, the weak correlations are a little bit more obvious. So from this example, there are a few things I hope that you learn or remember. Use colors, use markers if you have many data in scatter plots. If you have a lot of data to show, don't show the random correlated or the uncorrelated data because they're useless in your analysis anyhow. Focus on the correlation one. And if you have really important data, you can always choose more than one axis object, okay? So we can give each of the axes a different plot. I now skip the axis labels for convenience. Like this. 0, 1, 2. Little bit easier now if you separate. So whatever you do, again, choose the tools that are appropriate. By the way, this is a little bit messed up, right? The axis ticks and tick numbers overlay with the other plot. We have a few options to fix it. First of all, we could say share y equal true. Comma. Is it doing something? It's probably not share y. So with share y, the y-axis is the same, it's shared among all the different subplots. So this is one way of fixing it, but this only works if the y values are all similar. If they are very different, then it is not so nice anymore because we have a lot of y space, right? So what you do instead is you cannot share y anymore. Well, you adapt your axis a little bit. You go to figure dot tight layout. As an attribute. Was it with underscore? There we go. Okay. So, but again, your plot must be correct, must be proper, presentable. This one would be, except the axis labels are not there. Let's fix this very quickly. I have now 1, 2, 3 different axes or objects. It's always the same y label, right? So in principle, it's sufficient to put only one y label on the very left plot. But what do I do with the x label? If I put here 0, right, it's only on one plot, on the first one. Then I need to copy paste 2 times and are done. What about my x label change? Need to do every time. So no, we use a list comprehension, right? For I in whatever. So I.set x label in axis. Quick and easy. Not working. Why is it not working? Because when I talk and write, I always forget the for I something something. Okay, good. Now it's done. So far, so good. So now we have a proper plot. Y label, X label on each of them. Nice numbering, all the plots are visible, strong correlation, weak correlation, whatever. We also now can, well, to be fair, it still can be done better. Do you know how? What's missing? You put this in your thesis. You give your thesis to me to review. What do? I will say, this is not acceptable. I don't know which figure is which. Right? Why not? Why don't I know which one is which? What's missing? Well, you want to tell me that which figure is A, B, C, right? Okay, so how do you do? What do you do? Did you learn today anything that you could use? Yes, title, but title goes on top, right? I like to have my annotations actually in the plot, A, B, and C over here. Legend, how? Then each one has a different legend. Label, legend. How? Okay, I try. For which one? 0? Like this? Oh, what is going on here? Like this? So you can, in principle, change this order here, right? Because you said legend, I want to elaborate on this. We can turn it around, but not optimal, right? And then we need to change the y share back. Now we have one x, but many other y's here. So let's go back a little bit. So that is not saying it cannot work. You just go different direction, put in some other work. All right. So now I remove this. How about we use annotate? We do one together. Okay. So axis 0. No. How does it go? Does my autocomplete work? Never works. Go up, go up, go up. Markers. Annotate here, right? And then just copy. Well, shall I also copy the arguments, or do we remember? Font size and XY. So go down. Paste. What we want to call it, A, right? Font size is what? 8. XY is what? Well, we explored how to use XY. It's in absolute coordinates. So we could put it at -2 for X, and let's say 2 for Y. Okay? -2 and 2. So far, so good? So A is here. Seems a little bit off, right? We shifted a little bit to lower X values. -2.4. How this is like a 2.8 rather. Where's my X? X go from random points. Are they scaled? Okay, right. How about we are clever about this? Minimum of x1. Okay. So far, so good. So here's A. How do you do B? You copy and paste, and we started at 10, right? So your next break is only at 11. So you still need to work with me for like 20 minutes, right? Okay, so we try to not hard code as much as possible. So we try to iterate, right? So and then what is A? We can't have A all the time. How do we go from an integer to a character, Unicode? Is it odd or is it car? I always remember. Character, I, is it? And then for A is what, 96, right? But, you don't need to remember these things, right? You just, well, in principle, you do odd of A is what, 97. And then you have the position of A. So what you do is you character that, right? So you get your A back. And to get the B, you just add a 1 to that. So you don't need to remember what is A. You just need to be clever about it. So far, so good. Then we take this one, we put it in here. Is that right? Yes. Here, and this is already a string. Then we concatenate this string with the bracket. And we need to loop over I for I in the length of my access object. So far, so good. Can you follow what's going on? And then we close the list comprehension. There's a small error somewhere. Int is not iterable. Why is int not iterable? For I in int is iterable here. Plus I. Oh, must be a range, right? For I in. So the error here is this is just an integer, right? It's a number. But the list comprehension loops over a sequence. Right? A number is not a sequence, a number is just a number. To make a number to a sequence, we can use the range function. That gives us the sequence basically from 0 to 1 before that number. So far, so good. Now we have BBB because this one must be plus I. Okay. A, B, and why don't I see C? Zero, 1, Because I shifted my data up. You see this? The position over here is always 2. But the annotation is being, well, the plot here starts at, I would say, like 9. So we do the same thing. Finding the corresponding y value of my data distribution. So now very careful. The data distribution is always different. So we would actually need to tap into the data itself. Not really want to do this right now. Goes a little bit far. So we go back to our original positions. That would be max 2.5. We put this, scale this back, and then we have A, B, and C over here. So far, so good? Or you do it by hand. You can do this as well, right? Just put A, B, C annotation by hand. I think I lost you now, right? Did I lose you? I feel like the energy of the room is very low. Too much English, too long commands here, right? So one more time, right? So what is important to know? You can add annotations, right? You don't have to do it how I do it. You can do it stepwise. So you do 0, and then here you just write A, and you put the right position. I don't know, you leave it. And then you do the same with B and C. Okay. 1, 2, B and C. It gives you the same result as my list comprehension over here. Just like this is called hard coding because it's always like this, right? I change something, I change to 4 plots, it will not adapt. I need to copy paste again. My solution is adaptive, right? It's not hard coded, meaning if I have 4 plots, it actually should do this. Let's see, make a 4th plot. Hey, you can explore this yourself, right? You have the example, you took pictures, you have the videos. The important thing is you know how to get this result, right? A properly labeled plot that you can present in your thesis. How you go there, up to you. Okay, then example marker sizes. So here we have 4 plots. Right, again, my correlation data, right? So what's important? Here we have a 2x2 matrix. We have the axis objects. We give titles this time. We don't use annotations to make them distinguishable. Because we only have one data set in each plot, we don't need a label. We could have, but we don't need. We have proper X labels on the left and right. That is done hard-coded in line 14 to 17. And then, oh, yeah, this one is new. Line 18. PLT subplots adjust left, right, bottom, top, white space. W space is white space. So what does it do? Let's see. I plot it without. It's okay, right? A little bit much white space between left and right. Maybe, this is funny. So weakly, negatively correlated. Looks like first tick is weakly, second one is negatively, and third one is correlated. Weird. Let's go back here. Still, so I have adjusted with these arguments, left, right, bottom, top, how much space I have between the figures. Let's increase the white space a little bit, 0.5. Okay. Well, this is the width, h space, right? Horizontal, let's say 8, 0.8. Okay. So so W space is not white space, obviously, it's the width, the space, and the width-wise, and H space is the width or the space horizontally wise. Height? No, height and width, yes. So with H space, I can increase the spacing from top to bottom, or vice versa, in my plots to separate them a little bit, and with W space, the width space, you can separate them like horizontally, like from left to right. Okay, and the rest is basically known. Now what else can be improved? The hexagons and the squares are a little bit large. It's hard to separate them. So ideally, we would take the plot and we would make the marker size a little bit smaller. Okay, a little bit better. I still see some lumps of data points on the hexagons. Okay, maybe like that. And so my data points are not covering it. Other data points. So range. Adjusting the x and y axis for the example above. Mm-hmm. 12 more minutes, so we have time to go over this. So we have the example above as a reminder, and the data points always change because they are random points generated and put into correlation. I don't think there's a difference here now. And this is just double, all right? So what we need to do to change the x and y ranges is set x lim and set y lim. And the argument is a sequence containing minimum and maximum. Okay. MPL is not defined. So try to execute one of the examples from above, the one with the cosine and the different marker sizes. It tells me here MPL is not defined, but MPL I normally import from Matplotlib. Very well, so this is also working. Right, in the example above. So shall we just explore what now axis dot set x limit dot is doing? So my x values go from somewhere from -3 to +3, right? So -3 to +3. Nothing changed. How about -10 to +10? Well, I can take control of this. I can change this as I like. Why would this be useful? Well, a plot like this obviously is not good because there's too much white space. But we can have axis.legend, right? To label our data. Now, if we don't set xy, my legend is overlaying with data points. You see that? Here on the top right, there are some green data points that are covered by the legend. The legend is semi-transparent, but it's still not optimal. So I can take charge of the axis, give the plot a little bit more space in now y direction. So I adapt. I see already y starts at -4, so I don't want to change this. And I give it a little bit more space. I see the legend roughly takes 2 units, so I say 4 plus 2 is 6. So maybe a plot like this will help to separate the legend from my data points. And it still looks kind of alright. So far, so good? Okay, so what else? So in the next plot, we also use set x and y limits. Let's set it back to 10. But we are actually introducing a new modification, and that is set major locator and set minor locator. So the locators work on the x-axis, right? On the x-axis. So here, the x-axis is now, well, it looks a little bit different. We have 0, 2.5, some thicker ticks, and some minor ticks, right? Some smaller ones that are not labels. Let's comment the set minor and major and minor out. We go back to our original ticks, 0, 2, 4, 6. We set the major tick labels. Okay, we still have those values. We explore what is MPL max n locator. What is this? Well, it locates where's the maximum of a particular label. Find nice tick locations with no more than n bins plus 1. Very good. So how does it work? So we find nice X labels. We don't have some funny values like 7.4567. We have nice ones, 7.5, rounded at 1 decimal. And we say we want to have 4 of them, right? And we get 4 plus 1, that is 5, 1, 2, 3, 4, 5. Very good. How about we have 10? So actually we can have 5 is good already, right? How about a little bit less? 4. 4 doesn't give me 4, right? 4 gives me 3. Because if I would have 4 inside, it might be not as nice. So Python is overwriting you there the option. How about minor ticks? Minor tick axis, again, we use the max n locator from the ticker submodule, and we say, hey, every tick should have 4 subticks. But in the end, this doesn't really work for us, right? 1, 2, 3. So we have some funny ticks here, right? That are not really nicely aligned with our major ticks. What can we do? We have 5. How about 20? Yeah, this looks very nice, right? So each major tick has like 4 minor ticks. So these minor ticks can help us to read off values on the axis a little bit more accurately. In principle, we can also have 40, right? Does it work? Yes. How fine should be the minor ticks be? Well, this depends on how accurate you want this. If you also want to have minor ticks on the y-axis, we can go to the axis object y part. There we go. So now we have major and minor ticks. If we don't want to have on the MPL tick locator, we can try, well, maybe not. Actually, should do like this. What else can I show you? You should be able to set the ticks by hand. So we have 0, 5, 10. Let's try 0, 5, and 10. Right. So we can't do this, unfortunately. 4. So axis ticks one more time. This is the part where we take control over all the different tick values on the axis. So we wrote the example with a sine and cosine function, right? So when we have a plot, however, with sine and cosine, we normally don't write on the x-axis 0, 1, 2, 3. We write it in units of pi. 0, pi half, pi, 2 pi. How can we do this? We set the ticks by hand through the set ticks argument. So the set ticks argument works either on the y ticks or the x ticks. And there are two parts to it. One, of course, well, let's shift this back. This is the original one, 0, 1, 2, 3, 4, 5, 6. The first call is set ticks, where we give the locations we want to have. I put here 0, pi half, pi, and 2 pi. Then I override. Where are the values or the locations of my ticks? You see this? 1.571. Is that pi half? Well, 3.142 is pi, right? That divide by 2, yeah, maybe, right? Then we have 6.238. Is that 2 pi? Yes. So Python seems to do what we want to do. But we are not there yet. We want to have actually properly written pi's on the x labels. So we call the next function set x tick labels. And so we now set for each of the locations of the ticks what we want to have, and a tick strings. So we have here 0 as one string. And then remember the LaTeX notation we introduced earlier, the $2, $1 start LaTeX, the next dollar ends it. And I put here /pi. And /pi, which gives me the symbol, the Greek symbol pi. Next one is just pi, and the last one is 2 pi. 2 here still works. Okay. And this is my result. So now for each of the locations, 0, pi half, pi, and 2 pi, I have a proper representation of the value. So it looks like I missed one value, right? Right here. So the one part of the plotting is axis should be proper, should be equally spaced intervals or logarithmic intervals, something with some sort of logic behind at least. And it looks like I missed a value. Oh no. So can you help me fix it? What shall I do? And after this we go to break. So what do I do to fix this? And so some value, first I identify what is missing. 3 over 2 pi is missing, right? So what can I do to introduce 3 over 2 pi? Well, I need to introduce it. Now, do I need to introduce it at the right position in my list of values? I don't think so, because it's a list of values and it will be evaluated as we go. What I need to make sure of is that each tick value corresponds to the right tick number. So if I don't have a one-to-one map between the set ticks argument and the tick labels, for example, if I need to map 4 values to 3 labels, then Python is like saying, well, something is not working. You give me 5 values in one of the functions, but in the other function you only give me 4. What shall I do? I don't know. So we take control of it, so we pass the values properly, but then be very careful. Again, garbage in, garbage out. If you are careful, right? If you mix up orders, it can go like this. Is it correct or wrong? It's wrong, of course, right? Because 3 half pi should be smaller than 2 pi. So the order between these two lists here, set x ticks and set x tick labels, must be the same. So either you give those values ordered, right? Then you can give the same order in the list of strings, or you keep the same logic in the being not ordered. Let's see, how can we solve this? We could use sort. Well, I hope you can use sort. Let's see. Sort is not defined. There we go. So NumPy is sort. We order the values from smallest to largest, and we keep the same kind of strings. So this is one way. Another way is whatever logic we used to provide the values, we apply the same one to both lists. Go here. So if you read now, it's 0, pi half, 2 pi, 3 over 2 pi. And this also should work. Bracket this one out. There we go. And now it's correct. Questions? All right, so you are in charge of your program.